Hello, so I'm introduced to Kolmogorov-Arnold Networks and to my extension using multidirectional joint distribution neurons. So the main goal of this extension is to be able to propagate in any direction, like here. So artificial neuron will literally contain a joint distribution model. So substituting some variables, you can get a conditional distribution in any direction. It can be used as extension of CAN for example, for multidirectional propagation and multiple others. So CAN is this very popular recently approach. Kolmogorov-Arnold networks started recently in this article by 8 authors with a lot of citations, like one a day since then. And in my extension, so I have started it like 6 years ago. However, I had lots of projects. So finally, this CAN success has motivated me to write this archive and recently update it. So it was second citation. So I will talk about this extension. Okay, so in CAN, we assume that we can just train these functions, these 5 functions that. So there is this representation theorem I'm talking in a moment that it is sufficient to use just summation and just this trained one parameter functions. And here I assume that the joint distribution is given by just a linear combination with polynomials. So there are some polynomials and there are some coefficients. These coefficients describe our joint distribution. And we will work on such joint distributions. Yes, so here is some grayness, some simple model of such joint distribution neuron that it literally contains some joint distribution and what allows it, for example, to propagate in any direction. So okay, so this kind of neuron tries to model joint distribution of its connections of neighbors. So allowing for multidirectional propagation. And very important that many more training ways. So standard CAN and multi-layer perceptron are trained with the backpropagation. For biological, use something different. We don't know exactly what. So the question is, what types of training ways can we develop? And this kind of joint distribution neurons allows many new approaches. The most interesting, I think, is the information bottleneck training. So I focus on. So in this approach, we try to find the content of intermediate layers. Yes, so don't just think about optimization of weights of the networks, but just optimize the content of intermediate layers from one side to maximize mutual information to the final layer, but also to minimize mutual information from the initial layer, because we don't want just to be similar to the end, but also we'd like to reduce information about the initial, so remove noise kind of, so extract only the crucial features from the input. So with this approach we talk about, we can directly train using this information bottleneck training. So there will be simple formula for mutual information, and it can be found with some just eigen decomposition to find the behavior, the optimal intermediate layers. Okay, so in comparison to CAN, so it can be seen, it will degenerate into CAN, the approach I'm talking about, if assuming only the pairwise distribution. So we have pairs of variables, we look at the distribution between pairs, but in this extension, we will get at triples. So we would directly have dependency between triple variables, like in this density, you see that there is a complex dependency between triples of variables. So here we will be able to do it, and also we can propagate distributions, for example. So there are many new approaches in kind of extended parameterizations to CAN. Thanks to this kind of parameterization of neuron, which allows to many new things. These new training approaches, multidirectional propagation, some constructs, inclusion of higher dependencies. So the main motivation maybe here is that the biological neural networks, we know that they use something different than just backpropagation used to train artificial neural networks, and are superior in many tasks like learning, especially flexibility, robustness. So the question is that what is this? What is superiority come from? Which looks like qualitative superiority. That just increasing the number of neurons is not sufficient to reach them. So maybe and biologically, fundamentally, there is this. They don't have unidirectional propagation like we train our artificial neural networks for, but they are fundamentally multidirectional. If there is a stimulation, then it goes in both directions. So biological mechanism is not restricted to one direction. And so the question is, what's hidden in this very complex behavior? And the model I'm talking gives a hope that maybe it's relatively simple. It could be biologically plausible as in Khan. This is just training of single parameter functions and just summation. So it could be biologically plausible, hiding very sophisticated mechanisms for this learning for multidirectional propagation. So hopefully, using this kind of multidirectional neurons will help us reaching the superiority, the qualitative superiority. Okay, so let me go to further. Okay, so here is this famous Kolmogorov-Arnold representation theorem, like from 1950s, 60s, and there are many extensions, obviously, which looks great. So we're taking a varied function, continuous, and it says that we can represent it as a sum of some like 2n plus 1 times n one parameter function. So it's amazing that naively, using Taylor, for example, you'd have exponential number of parameters to describe it, but it says we mean just a small number to 2n squared, something like that. So it sounds great. You'd like to use it for neural networks. So there are many articles. I briefly look. I haven't looked details of the proof, but they are usually not a constructive proof. So like some iteration which should converge to something. So it's not so easy to construct them. But there are some recent articles I've tried to, but I wasn't able to get the details. This Uronson operator. So there are also stronger claims that you have to just train some single functions. However, that they are said that this representation are quite topological. So they call it fractional functions. So finally, in 1989, there is cited this Poggio paper that this theorem is not relevant to neural networks, and I think there are many attempts, but very unsuccessful until this year article, in which they were able to train it. So here is some diagrams from this year article. So now there are lots of GitHubs, talks. So we say that there is just summation in this kind of nodes and trained one parameter function in this internal nodes, and the trained function here that they use B-splines. So there are some polynomials. So there are kind of local representation. Yes, we just describe what's happening locally. The question is, should we use local or global? So I mentioned in a moment. So it is kind of smoothen version of a function. They try to train for each vertex. So here is some training. So finally, they use this additional, this very sophisticated function. So it seems that training is kind of concept is not that simple. So that you have to use this kind of tricks, adding these kind of functions, and they show that they have not only training but also some sparification, that's pure pruning, that you like to remove low importance edges, nodes. Then also if they see some nice function like sign or exponent, they just try to feed some symbolic functions or relatively simple functions. So they finally get some expression. So we can see that it is nice for fitting expression to data. The big question is that is it good for some different type of task? And here is the talk of this first author. And he says that if the task is good for this kind of, so basically it seems that not really, and the main question people usually may ask is, can it solve MNIST? And so I have found two GitHubs. So one said that it needs like 200 gigabyte RAM to train MNIST. Second was much better, say that it can get quite good training. However, it had replaced these B-splines, these local bases,
with Chebyshev polynomials, so with global basis. So now functions define the entire behavior, which I believe is safer approach. I will also use in the approach I will talk about. So that's the question: should we use local basis or global basis? I think global bases are generally better, especially after normalization. I will talk about in a moment. Okay, so here is the summary from the article. And generally the training, the basic of the training is the backpropagation. However, we know that biological neural networks have to use something different, maybe some kind of, but more sophisticated type of backpropagation or something different. The question was, so it would be great to have more training options than just this backpropagation. And I will talk that there are many different options, like this information bottleneck, like here, that we have some two layers, and you'd like to insert some additional layer between them, optimized from one side to have the maximized mutual information to this final layer, but also minimizing the mutual information from this initial layer. So how to optimize this intermediate layer. And here for the proposed approach, it will be able to, you can find it in analytic approximation. So for biological, we know some basic mechanisms. There's like long-term potentiation, these Hebbian neurons that fire together, wire together. However, for high-level mechanisms, we don't know much. Yes, so something's happening, we don't know what. So the question is, what kind of mathematics hidden there? And that's open question. And so the approach I'm showing could be, I think could be plausible there, and has enough power to maybe reach the biological neural networks in the future. So maybe it could be what they are using. Okay, so some comparison between artificial and biological neural networks from some links. So there are links in the slides. I will give the link in description. Okay, so there are some basic differences, but the qualitative differences are the most important. Yes, so for learning there are very precise structures, formatted data. For biological, there are very robust and can tolerate ambiguity and some modifications of data, deformations. For memory, so separate, integrated, stored program, self-learning, so reliability, so the biological are much more reliable. Operating environment, so artificial, we have to well define the environment. For biological, it's poorly defined and often changing, so they are much more flexible. So you can see that maybe there are some qualitative superiority, that just adding more neurons like they do now, maybe it's insufficient. Maybe you should find a better qualitatively mechanism. I will try to propose some. Okay, so the suggestion is that biological are fundamentally multidirectional. Yeah, so while we train artificial for unidirectional, biological are fundamentally multidirectional, and that might be a part of this qualitative superiority line. I think so. And here is some so fundamentally indeed they have to, that if you make excitation, it should go in both directions, and moreover, if such two waves meet action potential, they will cancel each other. So it's quite complicated. So but generally they are multidirectional. So maybe you should try to copy it with artificial neural networks. Okay, so here's the approach I'm developing, and I think it's very nice for artificial neural networks. So I developing it, I don't know, for 6 or 7 years, slowly into multiple articles. I'm showing the next slide. But generally, this is kind of between standard statistics and machine learning. So standard statistics, we assume that we have some moments, and so it's very nice. They are interpretable, independent, unique, controllable accuracy. However, getting a joint density from them is difficult, and there is not enough information. From the other, you have these neural networks, machine learning as neural networks, usually. So there are some iterations, some problems with interpretation. There are many equivalents, like you can just permute the data. So they don't control the accuracy. There are many issues. So let's try to do something intermediate, try to combining advantages. and this approach does it. So we still work on moments, mixed moments, but a lot of these moments, such that we can reconstruct them, the density. So we assume the density is given just linear combination in orthonormal basis, for example, of polynomials we assume here, and the estimation becomes extremely simple, just average over the same sample of the parameters. So instead of some complex iteration, just using this averaging, and you get the parameters, and they are independent. So we can estimate them independently, work on them, add more independently. So this is very flexible representation and very nice mathematically, I think. So there I have like more than a dozen articles. Okay, and so here is some one-dimensional example. So we have the sample with the orange points. Here we try to fit order 1 polynomial. So it only needs the expected value. So yes, expected value allows us to choose this function. Earlier we have just, so having no information, you can just use uniform distribution, assume here. So for having just expected value, we can assume this order 1 polynomial. Having also variance, we can fit, estimate parabola. Then you can add higher moments, third, fourth, which are very similar here as the variance, skewness, kurtosis. Not exactly, but very similar. So the question is, how many should we choose? So it is an extremely difficult question generally. So in practice, what I do is local likelihood estimation, cross validation. So how to choose the basis is a difficult question. And if you would use the degree to infinity, it would lead to the sum of Dirac deltas in the data set. So it will be overfitting, so we need to stop earlier. And you can see that very high degree, there are some issues with negative densities. So why density cannot go below 0, here it can. So in practice, there is needed this, I call it calibration, that we take, for example, maximum this density and 0, 1, and then we need to normalize, divide by this integral. So it is required, but it's relatively costly, this especially this normalization again, to requiring integration. So here for neural networks, we will remove this. So we just forget about this issue I mentioned in a moment. Okay, so here is a brief derivation. So how it is done? So we take a sample. The blue curve is the smoothen sample with density estimation. So we put a Gaussian in every point of the sample, Gaussian of what width, and here is this width. This is very, very narrow Gaussian. Here is very wide Gaussian, the blue curve. And having such G epsilon as the sample smoothened with density estimation with this Gaussian in every point of which epsilon, we would like to fit the best parameters of just linear combination. Yes, the question is, what A should we choose? And we use this mean square error optimization. So we would like to minimize this integral. And there is some issue here, is that this term will go to infinity when going with epsilon to 0. What is useful to get this epsilon to 0, like here, to get the most sharp picture. However, we are not interested in the value of this function, only in these a parameters. So we just remove this term, and doing so, and assuming orthonormal family. So here is the orthonormality condition. The estimation becomes super simple as just aj equals average over the sample of given function. Yeah, so we get this super simple estimation. So we also see here that especially at least for a compact support, having all these moments, they will define the entire joint distribution. However, it turns out that if the support is not compact, there are some pathological examples. Here is a link to an article with this function, for which all the moments do not distinguish this function. However, it's crucial. It is very important to go to a compact support. We do here. We go to 0-1 support for normalized 0-1 support. That's what is very, very convenient. Okay, so let's look at this normalization. So to normalize from some any distribution, like here, some Gaussian distribution to uniform on 0, 1. So it is popular for copulas. So economists like copulas. So this is kind of polynomial copulas. What I'm doing here. Okay, so we normalize by just going to this CDF. So we could parameterize it as, for example, assume Gaussian distribution and just find the width, the center and the width of this Gaussian, and go to this cumulative distribution function. So it is kind of subtraction, the mean and division by the standard deviation, and then going through this this cumulative distribution function of this Gaussian 0, 1. Yeah, so it's very similar to using Gaussian. It's very similar to just subtracting the mean and dividing by the standard deviation as what is standard normalization. So we need this kind of normalization, which is not very difficult and can be put into table. It can be used parameterized like for Gaussian. So we normalize each of the variables into this uniform distribution on 0, 1. And here are some such points from some economical data after this normalization, so pairs of points. So in 0 approximation, there are from uniform distribution on 0, 1 squared. But here is adding these four functions. So then we get some density shown with these isolines. Which is better. So I'll show why better in a moment. So here is using not 4, but I think 100 parameters. So looking at these parameters, so what they say, so the 0th parameter say that the density is uniform. So it's just for normalization. Yes, the 0 is for normalization. Then we done at 1, 1, which what it says that if it's positive, then going right with the variable, the expected value of the second variable goes up. Yes, so these kind of correlation coefficients, it's very close to indeed to correlation coefficients. Then you get the further dependencies. So then is, for example, how the variance. So we can see that the variance is different here. How the variance grow with change of this various variable. Here is the opposite. Here are between variances. So it's homoscedasticity, for example, in economy. That if one company has large change, then others probably also have large changes. Yeah, so we literally decompose the dependencies between 2 or more variables into higher and higher, into various types of dependencies between moments. So mixed moments which define these contributions to the joint distribution. Yeah, so this is very simple and very powerful representation. Okay, so here is some comparison with this kind of density estimation I also mentioned. So here are the points, and the question is what joint density they come from. So here is current density estimation using different widths of this Gaussian, spherically symmetric. And here is for using this polynomial basis. So how to compare them? We need some evaluation. So a basic evaluation is log likelihood, just averaged logarithms from density in the points of the data set. But we also need to prevent overfitting. We also need to add this cross-validation that we separate the training and test validation set. So here is some evaluation, log likelihood in tenfold cross-validation. So 0 would be just assuming density equals 1. So this is our baseline. So we can get above this trivial assumption. And we can see that density estimation for varying widths can barely get above. So sometimes it can get above, but usually it cannot. So it's not much better than just assuming uniform distribution. Why these polynomials, cosines, we can see that there is some change. So here it's different degree of the polynomial, of the number of cosines, this DCT, this cosine transform. So we can see that from looking at this plot that we should use degree 4 polynomials. So kind of use up to 4th moment. So expected value, variance, skewness, kurtosis. So this is the from data, economical data, at least this is usually the best assumption, and indeed I usually go to up to 4th moment. So why it is better? So in current density estimation, we assume that the new points will be close to the old points. Yeah, so we just put the Gaussians in all the points, and we assume that new points will be very close to these old Gaussians. But in contrast, this polynomial is asking for moments, so asking for some high order behavior. So intuitively it should be better for generalization than just assuming that new points will be close to the old points. So indeed, this is the proof, cross validation, that indeed it is much better. So the density estimation can barely go above trivial assumption, and the proposed using polynomial copulas kind of can handle it. If there is some dependency, they can indeed some extract it and show in an interpretable way. Yeah. So if there are very subtle dependencies, you can still work with them. While for KD, it's nice in one dimension, but in two and higher, and the density estimation is very poor. Okay, so here is the basis. So we have them for one function. We have these orthonormal polynomials, legend polynomials. So here is the zeroth polynomial is just equal 1 on 0, 1. There is the first, second, third, fourth. And we get this square. So looking at the first row, as there is 0 here, then it does not depend on this vertical variable. So it only depends on the horizontal variable. So it literally describes the marginal distribution of this horizontal variable. And also here we have description of marginal distributions of this vertical variable. Yeah. So and here are the mixed moments. So here are the dependencies. Here are just description of separate variables. For 3, we get marginal distributions, we get pairwise distributions, and then we get also triple-wise dependencies. Yes, so triple-wise means that if the two variables are large, then the third variable should be larger or larger more. For example, this is the simplest triple-wise dependence. So the question is, which should be chosen? Should be included in our consideration. All have very nice interpretations. Then we can draw these densities. Okay, so for CAN we go up to pairwise, and here we can go to triple-wise and higher. But you're going to higher, the problem is that the size of the basis grows exponentially. So there is a problem with size of the data set and overfitting. So there are difficulties. That's the difficult question. How large basis should we choose? So yes, so that's an open question and difficult problem to optimize among. Here is some situation in t dimensions. So again, we say that the density is again linear combination in this product basis of these legend polynomials like here, and so the estimation, this basic estimation, mean square error is just this averaging over data sample of the function. So super simple and independent. But you have also alternative ways of training. So the alternative one is that for example, in this average, all points have the same weight. Instead, we could say that we have also time, and say that the close in time have a high weight and far are low weight. So it is we can just replace this averaging into exponential moving average, and we get a model of evolving joint distribution. Yes, it works very nicely. So not only static models, but also this adaptive model that we can our neural network can be adapted on the go based on data. Another nice property that, for example, you could work with missing data. If you have an index, all these zeros means that there is no dependence. Yes, like we have shown this marginal. Yes, so there is no dependence because there is zero in this index here. Yes. So if there is no dependence, then we can estimate them for missing data if we don't have these values in our incomplete vector. So we can effectively work on missing data by just using the coordinates which have non-zero indexes. Okay, so here is the first view on this artificial neural networks, neuron from 2018 now improved, and okay, so this is a very powerful general neuron. So we have this neuron which have some inputs, and the basic question is what information a neuron can model. So it can model something, the description of its neighborhood, of its connection. So and the best description for forgetting about time in this moment is just the joint distribution. Yeah. So there is no more information about the neighbors than just the joint distribution. And this kind of neuron
using this hierarchical correlation reconstruction can model the joint distribution. So for example, and it can work in multiple directions. So imagine that it get some inputs, it can accumulate them, then update this model. Yes, so this is this exponential moving average to improve the model of joint distribution, and then predict as, let's say, expected value based on the input. Yes, so it could. So this kind of model has the joint distribution model of neighbors, update this model, makes prediction, for example, to get the value as just expected value based on partial inputs. Yeah, so that's the initial idea, and I thought about it through the 6 years, but wasn't motivated up to this kind of article. Okay, so here is some diagram from this updated version of this recent article. This archive. Okay, so we would have this neuron as having this joint distribution model. So here is this visualization of joint distribution. So we can do propagation in any direction by just substituting some variables and getting the normalizing and getting the conditional distributions. So here are some formulas. So we need this normalization. So there is required some normalization interlayers. They can be omitted, I will mention later. We defined the density as linear combination. The basic static estimation is just averaging. Here is for 3 variables that can be generalized. So here is this dynamic update with this exponential moving average. Then you can get conditional distributions. Yeah, so here is just substitute. Here we have normalization, and we get this kind of formulas. But if we want to work just on expected values, then we get this kind of formula. So we have some tensor, in fact, in this neuron, and we just perform different summation of this tensor. Yeah, so these are only linear operation of this tensor, and so we get this kind of formula. But if there is further normalization, then we can remove this 1/2 and this division, because so we can just work on this green part, because there will be further normalization which will repair it to make it as it should be. Yeah, so go back to approximately uniform on 0, 1. Okay, so we can also substitute in opposite direction and get this kind of formula, and it is very similar to CAN, because here you have just polynomial. Yes, so here are polynomials times coefficients that are trained. So we get one parameter trained polynomial here. Could be used different, like B-splines in CAN, but generally this becomes CAN if we just use pairwise distributions, pairwise dependencies, like here, A1J. So this is dependence between first moment of first variable and jth moment of the second variable, and there have to be 0 here. So if tolerating non-zero here, then we will get not only then we have polynomials of 2 variables. So it will be above CAN by including triple-wise dependencies. So the question is, but I think pairwise are sufficient by just using multiple layers to optimize the intermediate hidden layers. So I think pairwise are sufficient. Also for biological plausibility, I think it's crucial to use only pairwise, because so biological neurons, I think, could have trained these single variable functions and have summation. So this kind of like parameterization I think could be biologically plausible. But the question is how much can we squeeze from them, and with the proposed approach, we can squeeze much more. So we can do some basis optimization, and we have many more training ways. Yeah, so there is always this backpropagation. We can just treat it as parameterization and just optimize the parameters. So it is always possible, but we have also many other approach, like this, especially information bottleneck method. I will focus in a moment. Adapt propagation, so we can do some propagation of partial information, do some direct estimation using this formula like here. So there are many other ways. Finally, we can do this kind of tensor decomposition that treat this huge like from 4 variables to 1 as this huge tensor with 4 indexes, and try to decompose it as product of three tensor of size 3. So literally we can do this kind of training. So this is a quite developed topic. So maybe the tools optimize could be used here to optimize it, for example, the shape of the neural network. Okay, so let's speak about the so here we use this, there are used many approximations. Yeah, so the full approach is quite costly because of especially of this normalization, this calibration. So let's ignore this negative density issue. What simplifies a lot. So for neural networks, I think it's very important to just ignore it. So doing so, we can find this. So the density is like here. We assume that it's exactly no matter it can go to negative values. And we can get them conditional density by just substituting this y and dividing by the integral. So by normalizing, so we get this kind of formula. So we can see that there is this there is the same formula in the numerator and in denominator, but the difference is that there is 0. Why there is 0? Because for the 0 term here has to be 1. Yeah. So we need this kind of denominator to make the one coefficient for normalization for f0. Yeah, so this indeed we can get this normalization as very simple this way, and then we can get the expected value from this kind of formula. So calculating expected value only refers to the normalization term survives, getting this 1/2 plus the first term. We get this so here is from this integration, and we get this simple formula. So as mentioned, we can just use this above formula. So this is just polynomial. Yeah, so we get just polynomial like in Kant, but using polynomials like this Chebyshev polynomial. So similar to this GitHub is Chebyshev polynomial, but that it adds this normalization to 0, 1 uniform. So and we can propagate in any direction. You can switch the dependencies. Usually they use bias theorem for that. Here we do it without bias. Yeah, so this is very nice that we can do bias without bias. So you can use it for various bias scenarios. So and then using only pairwise for this kind of expected value conditional, you can see that we have this summation, and this summation using only pairwise, these coefficients are 0 unless if all three are non-zero indexes. Yeah, so only the two situations when there are zeros survive. Yeah, so the remaining are 0 because of using pairwise assumption. So this way we get summation of two polynomials, like in Kant, but using polynomials. Yeah, so indeed there is also needed this normalization, but generally you have summation like here plus one parameter functions. Yeah, so it is becoming very similar to Kant this way, but getting many more advantages. Assuming only pairwise, but we could also add triplewise. So triplewise would be with 3 indexes higher than 0. Yes, but we will get this product of two polynomials like here. So it is mathematically more challenging and probably biologically difficult to achieve, maybe impossible. Okay, so we get kind of like restricting to pairwise. We can add consequently add triplewise, and we have many more training possibilities. So that's I think a big advantage. Maybe getting closer to biological. So biological could have hidden this kind of mechanisms because it's relatively simple to express with simple mathematics. Yeah, so they seem biologically plausible, especially if restricted to pairwise. Yes. Okay, so I've said about propagation of values, but in real life we don't really often have values. So usually, yes, we know that there are 3 apples, but for example, working on, let's say, I don't know, height of a person, this is not a concrete value, but later some probability distribution. Yeah, so we just see a person, some shape, describe its shape. So maybe biological neural networks have also worked not only on values but entirely probability distributions. Yes, and this approach allows to work on probability distributions. So propagate through this network not only values but also probability distributions. Yes. So here is this formula for
for conditional distribution. So here it requires these functions of this y on this basis we are assuming, and to go to propagation of density, you'd like to replace concrete value of y with some density described by this BK coefficients. If you do it, so it needs some approximation that approximately this denominator is constant, and finally we normalize doing this approximation. So one of many here. So there are many approximations here. So maybe there are too rough. Maybe we shouldn't do it. So it will need experimental, but I plan to work on in July. So just replacing this value with this BK describing density, and we get propagation not of value, but we just work on probability distribution. Yeah, so this is much more flexible. It could, as biological, can work both on values and on probability distributions. So as we need. Here is some example for multiple variables. So basically, we having these values, we can interpret them as values. Can be values of as products, but using pairwise, it will be we have only single variables, but you can also replace it into these coefficients that shall be density, and we get the same network can propagate both values and densities. Remembering about some approximations. So again, biological can work with both. So maybe indeed this kind of mathematical mechanism could be used there. Okay, so finally, here we have just this summation over intermediate indexes. So here is some more sophisticated example that we have this huge tensor, and we just perform summation over intermediate indexes over these three tensors. Yeah, so we just have to sum it to be equal. So we get this formula by performing integration over these intermediate variables and using this constant denominator approximation. So it allows us to linearize the behavior of neural network. Yeah. So why it is known that linear neural networks are not so powerful. Here we finally linearize. However, there are non-linearities put into this function. So there are polynomials of degree second, third, fourth. So it contains non-linearities. So we need to use these non-linearities on the input and output of the entire neural network. And between them, just put this huge tensor and try to decompose it, make so finally this bottleneck decomposition to try to insert new layers between them. But finally, we have linearized the behavior, the non-linear behavior, but putting non-linearities in the input and output. And the problem is that it's huge tensor. So if wanting to use all the dependencies, it will have exponential size with the number of inputs, outputs. So it's not practical. So instead, we will have to add these additional layers, which finally need this kind of decoupling. Okay, so there are many new training approaches for such neural network. I go now to this information bottleneck approach. So we can use so we can treat as parameterization use standard propagation as always. Yes. But we know that biological don't use something different. So maybe you should search for some new approaches. So here we can do direct estimation, super cheap. Just averaging, yeah. So I'm showing it's much even simpler. It can be represented as even simpler. You can update the parameters with exponential moving average. Yes. So we have multi-directional propagation. So maybe let's take the output, propagate it back, and train intermediate layers using such propagated back data. Yes. So we can do it here. So we can have tensor decomposition approaches. We can from some base optimization. Then we have this information bottleneck. So we try to directly optimize the intermediate layers. So I will talk in a moment. So we would like to optimize this content of these intermediate layers. Okay, so let's look at this. Let's go to this information bottleneck. So this started by this by Teachby, this very important work. So generally this information theoretic view.
that having these layers. So in fact, we have a Markov process between the layers, yes, because the next layer has only information about the previous layer, and to the higher depths we can go to this. So, and it's very important here to use the information theorem, that we use mutual information as the best, I think the best way to evaluate the amount of information. So it is depend. So using mutual information, we can freely permutate the data. We can add some bijections, and the mutual information will be the same. So it is literally the number of bits X says about Y and or Y about X. So it's I think it's, wanting to do it right, we should use the mutual information as our evaluation criterion. And here is such an example that maybe indeed optimization of these intermediate layers is crucial. That we have some simple data, and we try to optimize the content of the intermediate layers. Yeah. So from one side, this intermediate layer should allow us to reconstruct the final output. But from the other, you should remove unnecessary information about the early layer. Yes, so there are both. There is this prediction of the final value and compression of the initial value, removing lossy compression. So removing not noise, unimportant data, extracting important features. Yes. So the question is how to directly optimize the content of the intermediate layers. Yes. So here is this more recent article, 2017. It has citations here. So yes, we would like to maximize both the mutual information between the current layer and the final layer. So this prediction, we don't want to lose information about the final values, but also we have the compression. We would like to remove unnecessary information from the current. So how to we need to do both, and there are some analytical formulas for Gaussian for situation, multivariate Gaussian, where this optimization they finally use. So both maximization of this final mutual information with the final value and minimization of the mutual information with the initial value layer. Can be done for Gaussian variables with the canonical correlation approximately, what is singular value decomposition of white and covariance matrix. So here I get analytic formulas which are different, essentially different. And so here we directly optimize them. So here is the nice evolution of during the training. Yeah. So here is this mutual information from the initial, and here is from the final in the vertical axis. So here is the first layer. So the color means the number of epochs. So the training, it evolves with the training. So we can see that the first layer has all the information about the Y, and only reduces information about the X. Yeah. So here is this compression is going left. Yeah. So this removal of unnecessary information, this noise from the input layer. And here is the final layer. So here is the final layer. So it starts. Oh, no, it starts here. Yes. Oh, sorry. It starts here, and it go up. So we can see that it improves the information about this the outcome we would like to get. Yes. So indeed it's trading. And depending on the number of information. So here is with a lot of information. Here is for insufficient information. So there, you can see that there's some overfitting, some problems. Okay, so let's look at the information theorem and mutual information for this hierarchical correlation reconstruction approach I'm talking about. So we assume that density is given by us by these linear combinations. And so entropy, Shannon entropy differential, so is given by this integration over this dimensional cube. Yeah, so hypercube. So it has this logarithm. So to get analytical formulas, we have to approximate this logarithm with just the first order time. Yeah. So using second order, it will become much more complicated. So this is another third, I think, crucial approximation we are using here. So maybe we shouldn't. Maybe, but the question is,
here the mutual information is some arbitrary evaluation. So this is very similar to mutual information. I think it has similar properties. It's not exactly the same because of this approximation, but should have similar properties. Okay, so here is this entropy. So we have this integration, and in this integration, we have the original basis and B plus as the basis without the zero, corresponding to the normalization. Yeah, so this one we have to remove to use this approximation. So we have to use this B plus basis here. And now we use the orthogonality of the function and just leave, and this integration survives only on the same terms. Yeah, so we have to multiply the same terms, so we get the squares, and so we need to sum over all the squares, and we get this approximation of this entropy of this multivariate variable x. Yes. So the same you can do for a pair of variables. So here is this entropy for this the joint distribution. So we get the same, and here we have just removed this zero as previously. Yes. So this normalization for this approximation, you get the formula. So we can also get some conditional entropies. So we need to be careful about these pluses here. So we just have to subtract this entropy from this y here. So we can get this kind of formula. And finally, the most important is this mutual information. So which is, I think, the best evaluation of dependency. So it says how many bits of information one variable says about the second variable. Yeah. So no matter, we can permutate the variables, we can perform some bijection, and still we get the same value. So this is amazing evaluation. In practice, the bijection should be monotonous later. Okay, so okay, so here is the final formula. So we get only summation over this B with pluses. So without this trivial, yes, so because to remove the marginal distributions, and so it is summation of it is this L2 norm for all non-trivial mixed moments between x and y. Yeah, so just remove all the marginal distribution information. Just take the non-trivial. That means that there is no zero in here nor here. So and make the squares and using given basis. It depends on the chosen basis, obviously. Yeah, so it would change if you change the basis. So again, optimization is very important and difficult, and we get this very nice evaluation. And let's go to this calculation of this final formula for information bottleneck here for this hierarchical correlation reconstruction neural networks. So let's look at these two. So we have this again. So we have this X layer, Y layer, and you'd like to fit some T layer between them and optimize this T to have a lot as much as possible information about this Y layer, but also as low reducing this information about this X layers. Yes. So here is the. Oh, I don't have it. Okay, so you like to optimize this information bottleneck. Okay, so this kind of formula, yes. Okay, so let's squeeze the features of the X variables into this one matrix. Yeah, so so there is I, it goes over the batch. So we can use size and batch, and J, and use in its basis BX plus. So we found this trivial zero. And the same we do for y. So we have again this basis. So this square root of n is for normalization. It will be clear in the moment why. Okay, so then use this MSI estimation of all the connections. Yeah, so we assume that there are all the connections between x and y axis, x and y layer here. Yes. So this way they create a matrix. So what are the parameters of the matrix? It is just this trivial product. Is this x bar t transports y bar. Yes. So just doing this, it will average over the data sample because it has this 1 over n because of this normalization factors. Yes. So this trivial formula, this trivial looking just product of the two matrices gives the estimation of parameters. All the parameters of this size of basis.
Yeah, so now we get the parameters of the neural networks just estimated by just this product. Then mutual information, as mentioned, will be this product here. So we just have to we just have to multiply. So the sum of square of these coefficients. Okay, so let's go here. Yeah, so we have these non-trivial xy moments, and we need to make the the squares, and it's becoming just a trace of matrix times transpose. So using this cyclic property of trace, we get this subtrivial formula where CXY is given by this X transpose. So it looks like kind of covariance matrix. So it's suggested to subtract the means. Maybe it should be done, maybe don't. I'm not sure, but probably the value should be close to zeros. And they are not just covariance matrix. So instead, this is a kind of similarity matrix inside the batch. So this is n by n matrix, which says that what is similarity between given point and given by taking scalar products in the feature set we are using. Yeah, so this is quite sophisticated. So this is kind of similarity matrix in our batch. So we'll work on this kind of. So I couldn't imagine at the beginning, but it makes sense that we have all these points, some abstract points, and the question is, what are the dominant directions inside this set of in our batch, in the current batch? So we work on batches here. So okay, so now you'd like to find this layer T. Yeah, so find optimize content of this. So for each of these n points from our batch, you'd like to get some values as its features inside. So here is this optimized information bottleneck formula we need to optimize. So using this formula, this approximation, we get this formula. Using linearity of trace, we get this looking simpler formula. Yeah, so we get this Cx and minus beta C. Oh, so it should be CCY. Yeah, I will repair in mode. Okay, so this is the CY. So we should diagonalize this X minus beta times CY. So we find we need to minimize it over the CT. Yes. So let's denote this CT. So we should just diagonalize this matrix, which is quite different from the Gaussian situation. So in Gaussian situation, we get this covariance matrix. We just subtract this n by n matrices with the beta giving the weight and find again the decomposition. And so now we diagonalize this matrix. So find this O, this rotation, new basis. And now for CT, we should use the same basis. And now this minimization becomes just this formula. So we can see that if there are, so we need the big lambda has to be positive. Yes, because CT is positive, that the non-negative, okay, non-negative, but it's sufficient to use positive. Okay, so we could get minus infinity if there is some negative lambda. Yeah, so there is, so we need to add some regularization. Yeah, so we found the regularizer, we get to infinity, so it makes no sense. So unfortunately, this is some complication. We need to add this kind, let's say this kind of regularizer. Using this one, we can find the big gammas optimized as just this formula. So 0 if there is a positive, and it's proportional to this eta and value of this eigenvalue, original eigenvalue, as the for the negative eigenvalues. So now we should use all the negative eigenvalues. However, the number can be large, so it goes with the n size of the batch. So maybe it should be reduced to some k, some smaller k. So take only a few dominant eigenvectors. So there are 3 parameters, unfortunately, here. So there is this beta, the original beta from information bottleneck approach. There is this eta regularizer, but also this k. I think it should be a T-plus parameter that we have some number or maybe some jump in the values. So but it's more difficult. So finally, we get this T as these features for this intermediate rise optimized with this information bottleneck as this diagonal with this found eigenvalues, and use this O
matrix from this organization and taken some K columns. Yeah, so we get K features of this intermediate layer. So now they are completely abstract features. We don't have to know what they are representing. Yeah, so it doesn't matter because it's hidden layer. It has some information, but we don't have to know what it represents. But if you choose some basis, whatever base you choose, it will give us some representation. It can be both values of this intermediate layers, but also probability densities, joint probability density inside. So it's quite interesting that you can work on abstract features without interpretation. The interpretation will be given by choosing a basis. So now we can also find the neuron weights using this formula like above. Yeah, so the neuron weights becomes just this product. The bar is missing. So we can get the optimized neuron weights. However, so there are these problems that there are n by n matrix when n is the size of the batch. So later we cannot use the entire data set because it will be huge matrix. So we have to split it into batches and let's say find the weights and average these weights. Yeah, so maybe over many batches, maybe average these weights. So that's an open question. How do we try? So it needs further work. To be average over batches, maybe some exponential moving average. And also how to use it finally. I think that the most promising is the use of recursive. But we have this input output. If we optimize the T, then we optimize some T prime here and TB is here. Yeah, so we try to insert more intermediate layers, maybe based on some behavior, maybe not uniformly, and add more layers here and here and here. And hopefully it will lead to some very good representation. And finally, after that, we can do backpropagation to improve it. So yeah, so there are many questions, or maybe use it in some interlayers, so just take the three succeeding layers and try to optimize the content of this intermediate layer. So yeah, so maybe do some orders with the batches, go through this some neurons and try to improve it with the batch, and so on. So there are many options to do it. So yeah, that will require a lot of research. I plan to work in July, and I please welcome if you'd like to collaborate on that. So it's different than the Gaussian bottleneck. So I think this might be a new formula for information bottleneck training. And finally, this is the last slide. So once again, we know that biological neural networks use something different. So some kind maybe of backpropagation, but definitely different than what we do for artificial currently. So the question is what? And here, as we discussed, there are many options. So maybe what is hidden in this biological is one of these options I have talked about. So I think it's worth to explore. Yeah. And we can treat this HCR neural network as kind of like parameterization, but with many advantages. Yeah. So it can propagate in any direction. Yeah. So we can go up, go down as we want. Maybe go left, right, and so on. So and also biological can go in multiple directions. So I think this is very crucial property. Yes, this freedom to propagate in multiple directions. We can both propagate values or probability distributions. So again, biological have to work with both. Sometimes we have triplets, sometimes we have width of the tree and height. So we have continuous variables for which it can only work with probability distributions, and the proposed can work with both. Yes, you join distributions as you want. So it's much more flexible. Sorry. No, sorry. What's happening? Okay. Okay, so we can value some probabilities, we have interpretation, and we have mixed moments. Yeah, so these are just correlation, some common stochastics. There are very concrete interpretations of these moments. You can add to triple-wise and higher dependencies. However, I think it should be done with intermediate layers, and it can be done here. Then we have a specific evaluation of model mutual information. Yeah, so that's very nice that we can directly from parameters get the mutual information evaluation. So I think it's very nice for practical applications. Also, there are these new training approaches. I think this is the most important. Yes, hopefully covering what biology does. Yes, there is direct estimation, just averaging, tensor decomposition, more complicated. So probably biology doesn't do it. If you mentioned bottleneck, I don't know. Maybe it's too difficult. I don't know. Maybe it could be biologically plausible. Yeah, so generally I think, and this trained one parameter function plus summation is biologically possible. So I think it should go this direction. Yes, so look kind of like parameterization, but more powerful. Yes, like this one that the neuron represents the distribution of its connection. Okay, thank you for attention.